It's a pleasure to introduce Alan Little from, oh yeah, let me spotlight him in case you don't see him. 1 second. Okay, that doesn't seem to work. Alan, can you just say hi that everybody can see you briefly for a moment?
Yes, hello. Thank you, Arvid.
Okay. Yes, so Alan has studied in Oxford and Manchester, if I got it correctly, in history, so it's quite a step to a programmer these days. He's worked in several project management and consulting positions before he joined O2 Telefonica 2005 and is now for 15 years in there. Is now senior business intelligence analyst and is working a project with Szech from TNG, who is a physicist originally and is now senior consultant, has seen several projects at TNG side, and Gentner, who is a mathematician, did his PhD in Ulm and is now for 2 years at TNG, also working in Telefonica projects. And they're going to tell us some interesting things about how they got AI working on production in the telecommunications environment. One last final technical note, Zoom has a Q&A tool. I will focus on that for questions. Our speakers will try to answer your questions during the talk and also after the talk. You can also, for those of you on YouTube, you can also use our Slack workspace, the Track 4 channel, to start questions there. We'll also keep an eye out for that. And after the talk, because the meeting will have to close rather soon after the time box, you can continue discussions there. And with that, I'm looking forward to a very interesting talk by Alan, Michael, and Michael.
Thank you, Arvid. Yes, today's topic, as Arvid's mentioned, is automating machine learning in telco network operations. I will start by talking a bit about mobile telecommunications, who Telefonica are, what we do, how the 5-minute version of how a mobile telecommunications network works, and what can go wrong with it. We've been working for, I think, 4 years now with our network operations team, and a joint project between network operations and my department, which is the data analytics and artificial intelligence department, looking at ways in which we can apply machine learning, artificial intelligence techniques to troubleshooting the mobile things that can go wrong in the mobile network, which, as we will discuss in the course of the presentation, is a very, very 24/7 real-time world, and rather far removed from the academic background that a lot of current data science is still coming from and related to. And that brings with it certain challenges. I'll start with, who is Telefonica Germany? We are, for those who are not familiar with the company, we are Germany's largest mobile network operator by number of subscribers. We serve 44 million customers, so over half the population. We're primarily a mobile operator, but we do have another 2 million DSL fixed net customers. And the reason why I'm here, we have been a satisfied TNG customer for quite some time now. I personally have worked with employees of TNG for over 10 years in a variety of projects. And I must say it's always been a great pleasure. They've always been highly competent, highly professional, and also generally agreeable colleagues to work with. And that applies not least to my 2 co-presenters today, Michael and Michael. You can see some of our primary brand is O2. Some of the others on here that you may also be familiar with, Blau, Phonic, iYildiz, are some of the other brands that we trade under. So the 5-minute version for probably the majority of the audience who haven't worked in telecommunications, what is a mobile telecommunications network? How does it work? What does it consist of? It consists of the so-called radio access network, which is the part that actually interacts directly with handsets. We have approximately 25 locations covering the country and approximately 40,000 cryptic abbreviations, a base station, a node B or an E node B, The names vary depending on the technology for 2G, 3G, 4G, but these are all names for the network, the network elements that actually do radio communication with handsets. 25,000 locations, 45,000 stations. Those among you who can divide 45 by 25 will have noticed that there are typically more than one station per location. We have 2G pretty much everywhere, and then typically there will also be at the location a 3G and or an LTE station. These communicate then with the so-called core network. And the core network is where telephony logic takes place. So things like call routing, things like routing and interaction with the internet, checking, controlling subscriber access, charging, applying limits, all this kind of thing. And obviously the 25,000 locations all have to be connected with the core network locations via another complicated area of the network, transport, which is all of the fiber optics, lease lines, radio links. Typically, the high traffic locations in cities will have fiber optic links, but many of the more rural locations, it's still where it would be uneconomic to run fiber optic for tens or hundreds of kilometers, are still connected by line of sight radio links. In total, so across the radio access network, across the transport network, in the core, there are something of the order of 500,000 computers, network elements that perform some essential function in the network. And 500,000 computers do not all work 100% reliably 100% of the time. The core network elements typically are a couple of dozen locations nationwide. They are in heavily physically secure data centers. They have redundant power supplies. They have redundant communication links. They are typically redundant paired functions. Some of the major sites have operations teams on site. If a core network element goes down, it is very, very bad indeed, but that happens, fortunately, that is fortunately for the reasons I mentioned, extremely rare. So for us and in our project, we're mainly focused on the radio access network. It would not be economically viable to have full-scale data center protection redundancy for 25,000 locations. It would also not be particularly helpful for the actual purpose of the network. If you want to sorry. The purpose of the network is to carry out radio communications with handsets. Being behind a data center bunker wall would not be conducive. So these 25,000 locations, 45,000 base stations sit outside. These are the things that you see on masts, on hills, on tops of buildings, and generally exposed to the outside world. And if you're exposed to the outside world, things happen. People steal the cables. Towers get blown over, or trees get blown on top of them. Masts on the top of hills have a tendency to be struck by lightning. Things get vandalized. It's not always entirely easy to get to them when you need to do something. And last but not least, if you have a location that's gone down in the middle of the forest in the middle of the night, you might find that the technician finds entirely legitimate and reasonable reasons not to want to go there. So, therefore, we need a repair and troubleshooting process. So just to sketch how the troubleshooting process works, and then I'll talk about where we in our project are applying machine learning to improve aspects of it. The network obviously is monitored. The core network elements keep an eye on the base stations that they're responsible for, and notice if there's no signal coming from a particular location. The redundant paired network elements monitor one another. Data centers have tracking of all the components that are in the data center, and there are dedicated servers whose entire job is to simply go out and ping the entire network multiple times a day and see that everybody's there, or raise alarms for anybody who's not responding. All of this results in a total of over 1 million technical alarm signals per day. And these can be a huge range of things. Anything from a major network element has gone down, is not reachable, it's obviously immediately critical, up to, okay, my input voltage is fluctuating a little more than it's supposed to be, my fan is turning a couple of RPM too slowly, my room temperature is half a degree too high. Some of these things, as I mentioned, are obviously immediately critical. Some of them can mostly be pretty much ignored. Some of them are situation dependent. So if a fan is behaving a little erratically or turning a little too slowly in February, no problem. If the same thing is happening in August, then that could be a major problem. So the network monitoring system itself applies some prioritization rules, some filtering. But at the end of the day, there are many things that are in this gray area between obviously critical and obviously negligible, where a person has to look at it and make a decision as to how serious is the problem. If you have a group of possibly apparently related problems happening in the same area, then which ones, what's the cause and what's the symptom? This is the job of the so-called Network Operations Center, the first line support. This is outsourced in our case, and their job is to decide which problems require immediate attention, which ones are worthy of a ticket in the ticketing system. So of these 1.3 million technical alarms per day, there are 470 alarms or groups of alarms which are deemed to be ticket worthy, and I'm mildly surprised that our corporate press office allowed us to actually name this figure in the presentation, but they did. Of those 470, 120 are actual outages. So service to the customer down and somebody needs to urgently do something. What somebody needs to urgently do obviously depends on the nature of the problem and some decision making on the part of the first level support guys. They have some ability themselves to do reboots, minor parameter changes, that kind of thing. Obviously, if they think the problem is a physical problem out at the location, something actually broken, then the field service needs to go out and have a look and fix it. Or if it's some kind of software problem that's more complex than a simple flag or a simple reboot, then that goes to our in-house so-called back office team, who deal with the more complex problems and also maybe refer those on to the manufacturers. So maybe get Nokia or Huawei or Siemens involved. Whatever it is, hopefully then the ticket gets routed correctly, the problem has been correctly diagnosed, and the thing gets fixed. Which is mostly the case, but as one would expect, not absolutely 100% always the case, and this is where we come in as a project in the attempt to help matters. So what I've done is I've noted here a variety of use cases, a variety of points in this process where we, with machine learning support, can attempt to intervene. The project's been going, as I mentioned, for 4 years. Some of these are in production, some of these are proof of concepts, but they're all things where we're either doing something or where we've definitely seen that there is potential to do something. The first one is in the network monitoring area. As I mentioned, 1.3 million alarms per day. There's no possibility that the staff in the Network Operations Center, the first level support guys, can look at and analyze all of those. The current prioritization filtering rules are largely hard-coded, built on years and years of hard experience. There's clearly potential there through machine learning to support the learning what's critical in what circumstances, some kind of cause and effect diagnosis and so on. Next point, as is typical in large corporations these days, I already mentioned that the Network Operations Center first level support is outsourced. The field service is also outsourced, and we have a relatively minimal in-house team. They cannot physically check and read everything that goes from first level support to the field service, and they have the responsibility for managing both their outsourcers. So clearly, if, for example, if the field service says, okay, we're not meeting our targets because the input information that we're getting from the Network Operations Center is no good, then it makes it difficult to know, is this correct? Should we draw penalties for one of the outsourcers for not meeting their targets, and if so, which one? The current solution is that there is a small team in our in-house department that manually checks a sample of tickets. We are in the process of putting automated quality checks on all of the tickets. Similarly, I also mentioned the Network Operations Center makes the initial decision, where should the ticket go? Does this look like a simple software problem? Does this look like a complex software problem? Does this look like a hardware problem out at the location? There's a relatively small number of people making these decisions under considerable time pressure, and we're in the process of rolling out some model-based support which helps with making that decision. The tickets mostly get successfully fixed within the required time. Not always. Sometimes there are good and legitimate reasons for this. Clearly, if the building that the mast stood on has burnt down, then you're either waiting until the building gets rebuilt or looking for a location nearby where you can build another location up from scratch. Neither of which happens in a couple of days. Or perhaps you need some rare, obscure spare part that has to be shipped by reindeer from some secret Nokia location in the north of Finland. Sometimes, however, it's simply that the process has gone wrong. Obviously, we're a large corporation. There are multiple teams responsible for multiple potential aspects of problems. It could be that a ticket has simply landed in the wrong person's inbox. They can't do anything about it. So we have an entire team dedicated to prioritizing, escalating, driving resolution of these kind of long-runner problems. And again, we have a model in production which helps and supports that team in terms of looking at what's the problem with the highest customer impact, the longest potential duration if somebody doesn't do something. And then there's in effect, the opposite of long-running tickets, where somebody did some quick fix under time pressure, which maybe brought the thing back up temporarily, but a couple of days later, the same problem occurs again. which doesn't necessarily imply that somebody's not doing their job properly, particularly in particular the field service are under a great deal of time pressure to get service to the customer restored as soon as possible, and move on then to the next problem. They don't always have the time, the capacity to do a serious root cause diagnosis, and it does happen therefore that they sometimes do some kind of quick fix, and we have a pattern of troublesome sites that have recurring outages. And again, we have a model in production which when a problem gets fixed at a location, we predict the risk that it's going to recur again in a short period of time, and maybe somebody from our in-house team should spend some time diagnosing what the real problem is, what the long-term fix might be. First but not least, we also, a use case which I'll go into in a little more detail on the next couple of slides, service anomaly detection. The monitoring process is currently based on technical signals, so CPU temperatures, electrical input output, whether things are reachable at all via pings and so on. What we have looked at and have in service for a couple of years now is something that looks instead at the actual service KPIs to the customer. So how much data is going through at what speed, how many calls are going through successfully, how many calls are not going through successfully. And we sometimes detect things here that are not detected or not detected until considerably later by the technical alarming process. I'll show an example here of a 3G station. The time series that are on display here is firstly the call duration, and then the data volume that's going through the station, and then the rate of call drops. So calls that get interrupted not by the user but by some kind of technical error in the network. The blue line, the color scheme here is the blue is the thing is behaving normally as our anomaly detection algorithms would expect. Red is the thing is behaving abnormally, and there is no ticket open. So there's a problem that's been undetected as yet. Green is then that the thing is behaving abnormally, but it's okay, and therefore green because there's a ticket open and somebody's out there doing something. Amber is then that there's still a ticket open, but as far as we can see, the behavior of the thing is normal again. So what's happened here? On the 31st of August, the station starts showing a significant degradation in performance. So the call duration is noticeably down from what we would normally expect. The data throughput similarly, and there's a sharp jump in the drop call rate. But at this point, as yet, no technical alarm, probably because the thing is not completely down. It's still providing some service, but seriously degraded service. This is an example from before we went into production with this use case. So two days later, then there finally is a technical alarm and a ticket is opened. Technician goes out, does something. And because it wasn't entirely clear to the technician what the problem was, and he's not sure whether his fix was successful, he's then left the ticket open under observation for 2 days, just to see if everything's okay again. I should say at this point, the technical alarming system generally works extremely well. Cases like this are rare, but they do happen. And so our anomaly detection process has a value add in terms of potentially detecting them considerably earlier than we would otherwise see them. And what's the process around this? It's important to say that first of all, we're talking about serious data volumes here. we have, it's not simply a matter of a data scientist firing up their Jupyter notebook and firing up some time series algorithms and jobs done. The input data for this is we're processing somewhere in the region of 25 billion records a day, which all has to be gathered and taken from whatever format it comes from the operational system into a common time series format that we can analyze. Then we run time series anomaly detection algorithms, of which there are many. And then obviously there is significant data science input into what are the right algorithms for what times for what KPIs, what is an important, what is not an important anomaly. Which brings me then to the third point. The data are noisy, particularly for 2G stations out in the woods that don't have much traffic. The time series are extremely noisy. And experience over this and multiple other projects shows that simply raw statistical anomaly points in a time series generate far too many false positives, far too much noise to actually be usable by the business. So behind our time series algorithms, that we then have a range of we have a set of classifiers which attempt to group alarms and to say, okay, what is a problem that might actually be serious for somebody to look at, and those are then ranked and sent out to the operational team. Currently, mostly in the form of a AI person in the loop process. So in the majority of cases, our primary output is a Tableau dashboard, which somebody then looks at and makes decisions. We are, in some cases, moving towards actually direct automated intervention into the operational systems, but at the moment, still mostly person in the loop. And then based on the information that we give out, then hopefully somebody goes out and does something to fix the problem. And what's also important in terms of continuous improvement of our processes is that we also need feedback from the business. So was this alarm legitimate? Was this alarm sufficiently important for me to be worth looking at? Process improvement. So seven major steps to the process, of which really the second and third, so the actual time series anomaly detection and the classification of what is a serious anomaly, are classical data science, but it's classical data science based on 20 billion data points a day of input, based on having to be part of an integrated operational processes with very limited resources to do something about the signals that you're generating. There's a lot more to it than just running the statistical algorithms. And in particular, in this environment, as I already mentioned right at the beginning, network operations works 24/7. The service level agreed with our outsourcers for fixing a critical network outage is 4 hours. And what we agreed with the network operations team right back at the beginning of the project is that they therefore need model results from us from event to visible in dashboard within 20 minutes in order to be able to do anything useful with the information that we're giving out. So yeah, a lot more to it than just the data science part. Not that the data science part is in any sense easy or trivial, but by no means the whole story. And for the rest of the story, I'll hand over to Michael, number one.
Well, thank you, Alan, for this nice introduction to the use case and start of the talk. So what we see now is like the use case, and what we now want to talk about and show you is how can we get this data science use case to actual operational process. And there's a lot of questions popping up, like Alan already said. Where do we run the model? at Telefonica, we have a Hadoop cluster, so we might want to use that. We want to use the big data technologies like Spark, and for our real-time use case, we want to use something like Kafka. But the data scientist is working somewhere in his Jupyter lab, and there's a gap going from here to there. On the other side, it works 24/7, and maybe your data scientist, she's working just a 9-to-5 job and not during the weekend, so somebody else has to step in and do all the operations, and you have to make sure that even that person understands what's happening. But let's first take a step back, and I want to just explain shortly what is the data science workflow. Like, where does our project start? Like, the project starts always like with getting a use case. So we discuss with the department, in this case that Alan showed with the NT operations guys, like, what do we want to achieve? Well, we want to see network outages that affect the customer. And then what are possible influences for that? Like, there's something wrong, there's something, and how can we quantize them and how can we see them? So in this case, we, for example, decided on the download volume because that's a good indicator, or drop call rates, something like that. And once we know what we want to get and what we want to achieve, what we want to evaluate and detect or predict, we can start going into our data science workflow cycle, where the first step is like getting the data. So we decide which data we want to get, and then we need to get access to the data, which is a non-trivial part of the whole process, because the data can be behind firewalls, on some obscure SFTP server, or maybe it's in a database where you still need to get access. And especially in this network service and impact story, it was also about data protection. Can we actually use this data? Because of course the call data is something very personal to the user, and we need to make sure it's properly anonymous, so we can don't have any data protection problems there. And also in other use cases, this is even more of a problem. So we need to make sure that this is happening, and maybe we also need to combine some sources to get the information we need. But once we have the data, we can start evaluating the data. So the typical first data science step there is like doing some descriptive statistics. What kind of data do we have? Do we have numerics? Do we have timestamps? Do we have some text? Are there corrupted fields? Do we have missings? And especially which fields do represent the problem we have? So do we have any labels that we can predict or evaluate on? Because if we don't have those, it gets a lot harder to actually build a nice model that's doing what we want to do. Then once we've got a good overview over our data, we can start building the model, where I also include like feature engineering and feature selection. So from the data we got, what do we actually want to use? And maybe can we combine some of the raw data to create some new information? Like, new information might be in the time series use cases. We get like the time series, but the time series has seasonalities. Like on the weekends, there isn't less going on than during weekdays. And we want to take out those seasonalities with a seasonal trend decomposition. So we only have like the actual movements that are going away from what we would normally expect. So this is the first step of feature engineering. But also stuff like, if we have categorical data, make it into numerical values so our classifier can work with it later on. And then when we have done all that, we can decide on which kind of classifier do we want to do. Do you want to do something simple like a logistic regression, or do you want to do something intermediate, I would call it like a random forest, or go to the neural network, deep learning kind of thing, because we feel like this might be a good choice. And once we've got our model, we've decided on what to do, we trained our model, then we need to evaluate it. And evaluating the model is not only doing like evaluation metrics. So looking how many false positives, how many false negatives, how accurate is our model, or is like an F1 score, lots of things there going on that we can try and use to find out how good is our model, but also like a feasibility, which means if we don't do anything and we just guess, we probably have something like a 50% chance to get it right. But maybe we don't need a 90%, our model doesn't need to predict it in 90% of the cases correctly. Maybe 70% is already really good, and maybe even the best that we can achieve, and already gives us a huge business value. So we have to get approval from business that what we did is good enough and is actually doing what they expected us to do. And if there's still something to do, we just go into the cycle again and do this a few times. And to be fair, you always do it a few times. It's hardly working on the first try, but once your department you're working with is happy with it, you are happy with it, then you can go and productionalize it. And this is now where this gap is starting, because everything up till now was happening probably like in a Jupyter notebook, which is like a nice environment because you can do rapid changes. You can just take one little change and just rerun this part and not everything else. So you can have a really nice workflow in this experimental science workflow. But once you go to production, you want a more stable release. And you want to use the big data technologies, because up till now, maybe you just worked on a sample, a few 100,000 data points or something, but now you want to go to the millions of data points. So you got to make some adjustments in your technologies. So what does that mean? Well, that means like you call your software engineer, people like Szech or me, and well, we say, yeah, we can build you those use cases. So we build you some data loading steps, feature preparation, and so on. We do this for a few use cases. We notice we do a lot of copy pasting, but still it's all kind of custom. But what we actually want is like, we want common stuff. So to really reduce the time needed to bring those use cases into production, having those common steps is essential. Those common steps apply as well to like nice data loading mechanisms, like the feature preparation should be somehow working the same all the time. The model prediction should somehow be using the same steps and techniques. And also we should have like a starting dashboard in the end. If we want to visualize it, having like a nice entry that's always the same is a very good user experience. So you want to figure out what's your approach there as well. So what we came up with at Telefonica was something called the AI platform Atena, which is in use right now for the use cases you've seen. And there we decided we just want some input, and then it goes into our platform, and up from there, you only can configure the data preparation step and the model steps, and everything else is taken care of. How those are applied, if it's a batch, if it's a stream, you don't have to care about it. You just configure here what you want to do. And the results get pushed out to a data sink here, and which can then be accessed by a dashboard or pushed onto the operational system. So, but that's like just scoring. Now we said we want to be stable and we want to make sure that our model is good. So what we got to do is we got to implement some kind of model monitoring. Your model, since data usage, for example, in the use case we've seen before, network service impact is changing over time. People are using more and more data. So maybe our data is changing and we need to respect that in our model. So we need to monitor if it's not working anymore and retrain it when necessary. And for that, we need like good labels, which can either come from the input or come from the user feedback, because the user sees like, hey, this is not working anymore, this wasn't a problem, and can tell us that with the dashboard. And then we can manage those labels and use them for monitoring and automatic retraining. On the other hand, you also have like your DevOps stack on top of that, because you not only want to monitor the models, you want to monitor the whole process. Is everything running? Is it running at the times you need it? Or is maybe the data not getting in anymore? Is the data not getting out anymore? And where's the problem? So you got your DevOps team working on that. And now the main point how we decided to make this really nice and easy switch from data science to production is using plug-in building blocks. So these plug-in building blocks can be something like a simple analytics function like imputation. So you got missing values in your data, and you want to say like, hey, just replace those missing values with zeros, so my methods later on will still work. Or something like the seasonal trend decomposition we talked about earlier already can all go into this data preparation step here. So you just configure it, you put in, hey, this is my model I want to use, you configure that in, and then you can use this, and you can just plug in anything and any complexity that you want. And also for the training, you can define like we have an automated grid search that just runs regularly and tests a huge grid of parameters against the model data that we get over the time with the labels. You can say, hey, test these 5 models with these parameters, and he tells you, well, this was the best model and it was this good. And then you can push that to production as well. So far as that. So how do you configure this? Well, as software engineers, we thought like the nicest idea is to just use a YAML file, right? It's nice, it's clean, and we are even gone so far. So we implemented like a inheritance system for YAML files. So we have a config loader that just resolves this config first and then updates it with everything we write down here. So we got nice, clean, small configs. And as you can see here, we define our processes. So we're getting the scoring data, we're getting our training data, and then here we define like the data preparation step. In this case, it's a batch process. And here we define like the plugin building blocks we want to use. So we say we want to use the impute, the dummy encode, and the mean standard deviation scaler. And down here we define how they are actually configured. So for example, for the dummy encoding, we use the processor available on the source path. And these are the parameters we want to pass in. And as you can see now, this is a rather small and nice, simple thing. And for us engineers, it was like, yeah, this is nice. But what we noticed is like the documentation also needs to be there. So what is actually the parameters we can use, which are available, and also when working with business analysts and data scientists that are maybe not that code affine, like they not that familiar with YAML, they wanted something a bit more graphical. And Szech is now going to show you what we came up to solve that problem.
Okay, all right, thank you, Michael. We are a little bit behind time, so I'm trying to hurry up a little bit. So let's jump right into it. This is our graphic Atena configuration tool, and I'm going to show you how it works. So here at the top, we have some introductory description remarks. We can press on those buttons, and it will show you what you need for the start, for example. The high-level process ID will define the use case for the product. We also need to give the model ID. As of now, we cannot define the model metadata within this tool yet. And we also have to decide whether it's a batch or streaming mode. So let's select the high-level process, choose NSI, which is the network service impact Alan talked about. And it is a batch use case. So now we could load the config files from a YAML if they are already present, but in this case, we will start from scratch. So first, we define the data source. So we will have a table. For example, in this case, input table is network KPIs. In this table, we already have to know what are the primary key columns. If it's a composite key, we can add multiple columns here. In this case, we only have one primary key. We then could define a primary data stamp, which is optional and we're not going to do in this case. So now let's come to the real processor configuration where we do the work, the transformers, and the classifiers. As we haven't loaded anything yet, the list of currently configured processors is still empty. And we will now add one. A very simple one, for example, the presence encoder. It does nothing more than transform a null and empty values into 0 and everything else into 1. If we need documentation, here are also the links to documentation to read a little bit. And down here is the documentation for this particular encoder, which will also tell us what to enter here in those forms down here. Input count is quite obvious. You don't have to read it. It's the error code. So if there's an error code in here, it does have an error. If it's empty, there's no error. So this encoding makes sense. We will leave the suffix at its default value and now add this configuration to the list. And you can see it will appear up here. And now let's add a second one. This time we will add a classifier, which will do the actual classification. For this, we have the predefined model metadata in here, which is NSI-AL. And we will leave all those fields down there empty as per default. And now we can just add this configuration to the list of processors, and it also appears up here. Now we have defined two processors, but we have not really said yet where they will be executed in which order. And this is done down here with the feature generator and the class generator stage. They're two separate stages. We will add the first one, the presence encoder, to the feature generator stage. And we could, of course, add many more transformers down here if we had them configured. And then we will also add the classifier pipeline to the class generator stage. And then we're pretty much done. That's it. And we can save the configuration. It will produce a YAML file as output, and everything is configured. So those processors are really the core thing, those custom building blocks that Michael showed earlier. And let's just have a look at this presence encode processor. It's a very, very simple one. It just fits on this one page. And this, of course, works because we use inheritance. This presence encoder inherits from the processor base. And in the processor base, we do all the logic, how this is called and how it works. In here, we only define an init function, which takes care of the configuration. Remember, we just defined the input column for this as error code. We could have a simple column, or we could have many columns as input. And then everything else we need to do is define those two apply functions where the actual logic happens. We have two, one for pandas and one for Spark. They both accept a data frame as input and also return a data frame, so very simple. One of them, of course, is pandas data frame. The other one is a Spark data frame. In actual fact, we do not always have to implement the apply Spark function, because if we don't have it, if it's not implemented, the processor base will take care that even if we try to run this in Spark mode, so distributed amongst many cores, it will transform the apply pandas function to a Spark user-defined function and distribute it amongst the nodes. So that way, we are able to also wrap third-party transformers into our framework, because they usually accept a data frame, NumPy array or something, and return a NumPy array or something, and it's very easy to wrap this. Actually, we have done this for most of the, for all sklearn-like transformers. So everything that behaves like an sklearn transformer can be added with just adding 2 lines of code into our framework. But now let's take a step back from those 2 examples and from the demo and have a little bit of a higher level look at our framework code. So we do have a modular structure. We have a core framework with general purpose functionality. And this core can also be used, for example, in a Jupyter notebook. So everything that's available here can be already used by the data scientist in the Jupyter notebook. And afterwards, then it's also being used in the production process. So we have connectors, we have the configuration handling that you've seen before, and we have the analytic modules where the presence encoder that you just saw is part of. And then on top of this, we have 2 platforms, the Process Diagnostics Interface, short PDI. This is the time series data platform. So it is highly scalable, it runs in batch mode, always with Spark, and the data format is optimized for time series data. So it's really optimized. And then we have the General Diagnostics Interface, which is usually event-driven, can run in streaming or batch, and is, of course, not as highly optimized. We can implement more platforms on top of this if we want to. And I'm going to show you which technologies we need, or we're using currently, or the main technologies we're currently using. So as you've already seen, we're mainly using Python as our programming language. And we have Spark and Pandas as our main data engineering frameworks. As Michael already mentioned, we have Jupyter and scikit-learn and CatBoost as our data science technologies. For data storage, we heavily rely on Hadoop with Hive and HBase's interface, but we also have Kafka and Oracle connectors. For infrastructure and operations, we use GitLab, Prometheus, Splunk, and we're moving in the directions of using Docker and Kubernetes. And finally, for visualization, we use Tableau and Dash. Dash is also what we used for the configuration tool that I just showed you. So as you can see, most of these technologies are actually open source. And this made our life a lot easier when we experimented with going to the cloud. So currently our cluster is running on a local Spark cluster. And the idea was to just take everything and move it to AWS. So we chose an Amazon EMR cluster. We, once we could access to it, got all the data on it through the firewalls, which was a little bit harder in this big enterprise. Everything else was actually quite easy. We had to change a couple of configuration. We exchanged our Hadoop cluster with an Amazon S3 storage, which also was quite easy because we're using Hive as an interface. And then everything was up and running. Our PDI platform now worked in the cloud. And of course, we did some scaling tests on this. We increased the number of, we took actually the use case that Alan presented, network anomaly detection. And you remember we had like 25,000 locations. We increased this number to about 100,000, increased the number of measures, which gave us about 100 times the current amount of data in the cloud. We played around a little bit with the number of nodes, played around a little bit with the number of nodes, and we created a scaling curve, which actually was really quite linear. So this made us quite happy because it proved what we already claimed, that our PDI platform is very scalable. So to wrap this all up, what was the impact of the Atena framework on Telefónica? So we have plenty of use cases. We already talked about the network service anomaly detection use case quite a lot. We also have many other network use cases that Alan talked about earlier. So this is just a selection, but we also do have completely different use cases that have nothing to do with the network. For example, we analyze how users click through the online O2 portal. So those are the time series use cases. And we also have a little bit newer, the event-driven use cases, where we, for example, have the resolution recommendation that Alan also talked about, where we help the field force how to resolve problems in real life. With all those use cases coming in and even more coming in, it's really important that we can productionalize fast. And this Atena framework helped us to reduce the time for the productionalizing part to potentially less than a day. Of course, this doesn't mean that the whole time from idea to production is less than a day, but now the data science part can be the main focus, which is, of course, what should be the focus. And all the other things that data scientists don't really like monitoring and operations, is greatly simplified because we unified everything. And also, if we have improvements to those parts, it now affects all the products, all the use cases pretty much instantly, which just makes things a lot faster. And of course, last but not least, it enabled the simple transfer to the cloud, as we've proven. And this means even if we get more and more data and more use cases over the next couple of years, we will still be able to handle it. Thank you. So I don't know whether we have time for questions. I guess not.
Yeah, I was just going to get in. Thank you for this very interesting talk. Unfortunately, we basically just used the entire time box. The good news is you can get all the questions answered later if you just ask them in Slack. I have seen that many questions got answered who came in during the Q&A tool. We have one hand raise from Alexander Milinsky. I maybe can give you very brief voice. Did you actually have a question as well that didn't get answered yet?
I think Alexander answered one of the questions. Thank you very much for that, Alex.
Okay, great. Thank you very much. So yes, thanks for the very interesting talk. As I said, we're basically completely out of the time box, or just at the limit of the time box. I'll trigger a quick poll. It would be really nice if you could rate the talk. Sorry, that we can know where we can improve later. Feel free to ping us later about stuff that didn't work well. And I'm sorry for everybody on YouTube that we had a bit of delay of getting the stream started there. I hope you didn't miss too much. And if you kind of had unclear things because you lacked a bit of context, just use please Slack as well to get in touch there with the speakers.
Okay, thanks. Bye-bye.
Okay, good to see so many people here. See you in the next talks.
Bye.
Bye-bye.